Hello, oceanography students. For the video this week, we're going to be talking about tides. For this first video, we're going to learn about what tides are and the causes of tides, and kind of what we experience along the shoreline. And then for the second video, we'll learn about how the tide changes over the course of a month, and how the tide changes over the course of a year, and some different patterns that we see around the world. Okay, so first of all, what are tides? If you recall from our waves lecture, where we learned that tides are actually a type of wave. So tides are the periodic rising and falling of sea level. That's what we experience along the shoreline. And they're very long waves. So that means, again, a wave is a disturbance that travels through a medium. So when it's high tide at the beach, you have a wave crest at the shore, right? So that's the high part of the wave. When it's low tide, we have the wave trough at the shore. And so because they're very long wavelength waves, they're always affected by the bottom, which we'll get to really in the next video, the importance of that. Okay, so when the tide is high, in this harbor, you could actually, take your boat out. When the tide is low, your boat's on the ground and you can't get out. Okay, so knowing the tides is very important if you are a seagoer. Okay, so now what causes the tide? The tide is a distortion in the shape of one body induced by the gravitational pull of another nearby object. Okay, so in order to understand this, since we're talking about different objects in the universe, we kind of have to zoom out from our planet of Earth and look at the solar system. Okay, so here we have this big bright sun, and then we have 1, 2, 3. Here we are, the third rock from the sun, Earth. And you'll see that the closest body near Earth is the moon. And then you have the sun, which is the very large body that is near Earth. Okay, so it's going to be the moon and the sun that have the greatest effect on the tides on Earth. So essentially, tides are caused by gravity. Gravitational force, which is from Newton's law of universal gravitation, is shown as an equation where Fg equals the force of gravity. Capital G is a constant for gravity. M1 is the mass of your first object, so maybe Earth, and M2 is the object of the second, the mass of the second object, which could be the moon, divided by the distance between them squared. Okay, so if mass increases, then the force of gravity also increases. Okay, so that means the bigger the object, the greater the force of gravity. If distance increases, though, the force of gravity decreases, and it decreases by a lot because that variable, distance, is squared. Okay, and since it's on the bottom of the equation, then it means it's decreasing Fg, or the force of gravity. And since it's squared, it means that it's decreasing it by a lot. It's decreasing it by double what the actual mass increases it by. Okay, so that in itself would tell us that objects that are closer are going to have a greater effect than objects that are farther. And so the distance from the Earth to the moon is 384,403 kilometers. The distance from the Earth to the sun is 149,597,890 kilometers. Okay, so the sun is much farther away, but it's bigger. But because the distance is more important, that means that the moon is going to have the bigger effect on our tides. So again, periodic rising and falling of the sea level. Okay, so this little image is just a kind of a very simple image that's showing you the Earth with the gravitational pull around it. And so you can think of maybe this pink part as being the tide, and here you have the moon. So the moon is going to pull on the water that is facing it, and then also you have a bulge of water on the opposite side from the moon, of the Earth from the moon. And so that side is actually caused by inertia, which we'll get to in a second. Okay, so the bulge on the side facing the moon is caused by the gravitational force exerted by the moon on the Earth, right? The Earth, the land, is solid, and therefore we don't see the deformation of it as well as we do the liquid or the ocean. Okay, so that pull from the moon is evident by the bulge that it creates around Earth. And so, you know, if the bulge is over here, then that means that everyone that is over here, or anything that's over here, is experiencing high tide, and everything that is over here where the bulge is not, or down here where the bulge is not, is experiencing a low tide. Okay? If you're over here, you're also experiencing a high tide. So why is there a bulge on the opposite side of the moon, on the opposite side of the Earth from where the moon is facing? So for that one, that's caused by inertia. Okay, and that's the reason why in this image, this person who's driving this car crashes into the brick wall and flies out of it. Essentially, inertia is a fictitious force that is not really a force, it's just due to a change in something else, right? So the momentum is forward movement, right? But the car hits the brick and that causes the forward movement to stop. But the person in the car wants to keep on moving forward, and that's why they fly out of the car. So inertia is the tendency of moving objects to continue in a straight line. It's also called centrifugal force, but you don't need to remember that term. I would rather you just remembered inertia. It pushes you against the side of the car when the car turns quickly. So when you're driving in a car and you turn left and you get pushed to the right, that's not really you getting pushed to the right. It's that you were already traveling in that direction, but the car moved to the left. And that's why it felt like you were pushed to the right. Additionally, if you're riding in a car and you have a glass of water that doesn't have a lid on it, and you suddenly slam on the brakes of the car, the water's momentum was moving forward, right? And so you're holding the water, you stop with the car, and therefore the water is going to spill forward. And then if you then slam on the gas, you're at a stop, and now the car moves forward, the water is at a stop, and therefore the water is actually going to spill on your chest. Okay, so that's what inertia is. Inertia is exactly opposite of gravity. So the bulge on this side is created by the inertial force exceeding the gravitational force. On this side, gravity causes the bulge. On this side, inertia causes the bulge. Okay, so to simplify that, our tides are caused by gravity and inertia. Okay, so gravity and inertia causes the two bulges. So you can imagine that the moon is pulling on the Earth, and because the water is liquid, we see the deformation of it more readily. Now, on the other side, the whole reason why this bulge is out is that the Earth does wobble towards the moon. And so as it wobbles, the water that is over on this side wants to stay where it is, and the hard part of Earth moves away from it. Okay, and so that bulge is just created by the water wanting to stay where it is and the Earth moving away from it. Okay, so again, gravity and inertia cause the tides to occur. Okay, so let's go over a couple of things. One, the tides are a result of inertia and the gravitational force exerted on the Earth from the sun and the moon. The moon has a stronger pull on the Earth than the sun does because it's closer than the sun is, even though the sun is larger. The Earth goes through one full rotation in 24 hours, so we would call that a solar day, right? That is the amount of time for one location on Earth to be lit up and then go all the way around, be in the dark, and come back to being lit up again. But for the moon to rotate around the Earth, it takes 24 hours and 50 minutes. So that's a lunar day, right? Because The moon is moving around the Earth, but the Earth is also moving. So it takes slightly longer for the moon to be exactly under the same position or over the same position that it was previously. Okay, so a lunar day, again, is 24 hours and 50 minutes. It's 50 minutes longer than a solar day. So again, it takes 50 minutes longer for the moon to reach the exact same location over the Earth as it did the previous day. And so remember that since the tides are caused by the moon, we should be operating on the lunar day rather than the solar day. Okay, so at the shore, we have down here the shoreline, so we can see what's happening. Up here we have the Earth rotating around, and we also have the moon moving or orbiting around the Earth, so we can see what happens as the Earth rotates and as the moon moves. Okay, so our Earth is rotating beneath the moon. So anytime this location, which is what's shown here, is either directly under the moon or directly across from the moon or the opposite direction of the moon, we're going to have a high tide. Anytime the Earth is at a right angle, like over here or over here, we're going to have a low tide. Okay, so here we have a high tide, then you have a low tide, and then you have a high tide. Okay? So the bulges always face toward and away from the moon, and those bulges represent high tides. Our Earth rotates through the bulges, so there is a high tide, then 6 lunar hours later there is a low tide, then 6 lunar hours after that there is another high tide, and finally 6 lunar hours after that there is another low tide, to make up one full lunar day, again, which is 24 hours and 50 minutes. Okay, so at a given location that experiences what's called a semi-diurnal tide, that means 2 high tides that are the same height and 2 low tides that are the same height, in a day, you have a high tide occurring when the moon is directly overhead. The low tide occurs 6 lunar hours later. Another high tide occurs 6 lunar hours after that. Another low tide occurs 6 lunar hours after that. And just remember that 6 lunar hours actually means 6 hours and 12.5 minutes solar time. Okay? So if you're answering a question about tides from going from high to low in solar time, then remember that a change is going to occur every 6 hours and 12.5 minutes, because there are 50 extra lunar minutes in a lunar day. Okay, so if you take those 50 extra minutes and you divide it by 4, because there are 4 changes, then you would get 12.5 minutes. That's where that comes from. Okay, so here, to visualize that again, say that you're looking down on the North Pole and the Earth is rotating in a counterclockwise direction. Here's the position of the moon here. Okay, so we're going to go through a full day, 24 hours, 24 solar hours. Okay, so a normal day. Normal solar day, I should say. Okay, so we're going to start right here at midnight. So here is this island, okay, and the island is at a right angle to the moon. Therefore, the island is experiencing low tide, and the island is emerged out of the water. Okay, the Earth rotates, and 6 hours and about 12.5 minutes, it's just writing it as 13 here. Now the Earth is under the island, excuse me, is under the moon, and therefore it experiences a high tide, right? We go from low tide to 6 lunar hours later, a high tide. Okay? 6 lunar hours after that, the Earth continues to rotate, and now the Earth is again at a right angle to the moon. And so, excuse me, I keep saying the Earth. The island is at a right angle, and so again, it experiences a low tide. 6 lunar hours later, which now brings us to 6:38 p.m., the island is directly opposite of where the moon is facing. And so now we have inertia, which causes this bulge, which causes it to be high tide. And then again, the island is underwater. Okay, and then we continue. 6 lunar hours after that, we're back to being low tide again. Okay, so that's it for the basics of tides. If you have questions, please post them under the weekly discussion, and watch the next video for a little more about tides.